In this video, I'm going to use complex numbers to show the relationship between hyperbolic functions and trigonometric functions. Let's start off with some definitions. Over here, I've written the definitions of hyperbolic cosine and hyperbolic sine. These guys are both written in terms of the exponential function. E to the x can be used to describe exponential growth, and e to the minus x can be used to describe exponential decay. If we add these two functions together and divide by 2, that is, by definition, the hyperbolic version of cosine. The hyperbolic version of sine is given in a very similar way. The only difference between these two definitions is this minus sign over here. So the minus sign is associated with hyperbolic sine, and the plus sign is associated with the hyperbolic cosine. You can see that the notation over here is analogous to the notation for trigonometric functions. The only difference is we add an h over here, and that h signifies that we're dealing with the hyperbolic versions of trigonometric functions. We can also take these guys and define hyperbolic tan. And hyperbolic tan is defined analogously to the trigonometric version of tan. So in trigonometry, tan is defined as sine over cosine. It's the ratio of sine and cosine. And over here, we have the analogous definition. Hyperbolic tan is defined as sine, or the hyperbolic version of sine, divided by the hyperbolic version of cosine. You can see the h's over here are all to signify that we're dealing with the hyperbolic versions of these trigonometric functions. And if we take these definitions and substitute them into this definition, then what we're going to get is this relationship over here. So because there's a 2 and a 2 over here, there's a shared factor of a half. That factor of a half cancels when we take the ratio. So this top part over here comes from the hyperbolic sine, and this bottom part comes from the hyperbolic cosine. So there's a plus in the bottom and a minus in the top. So what we can do to this is we can actually write it in an alternative form. We can multiply the numerator and the denominator by e to the x. And if we multiply by e to the x, what's going to happen to these terms? Well, e to the x times e to the x, that's just going to be e to the 2x. That is using exponential laws. So we're going to have e to the 2x. But what's going to happen to e to the minus x when we multiply by e to the x? In the exponent, in the top, we're going to have an x and a minus x. Those are going to cancel, and they're going to give 0. So we'll have e to the 0, and e to the 0 is 1. So that's where these 1's come from, and that's also where this e to the 2x comes from. And the only difference is we have a minus upstairs and a plus downstairs. So this is an alternative way of writing hyperbolic tan. So now we have the basic hyperbolic functions. And you can see they are analogous to the trigonometric functions, sine, cosine, and tangent. You can also define other functions. For trigonometric functions, there are a variety of other functions you can name and define in terms of these functions over here. But these are sufficient for this video. Now let's go ahead and examine how we can link these guys to the normal trigonometric functions. So why is it that these guys are so similar? If we were to construct trigonometric identities, we can make those trigonometric identities work for the hyperbolic functions as well. The only differences are going to be an occasional minus sign. Why is that the case? Well, it's because of imaginary numbers. So if we take a perspective of the complex plane, so if we imagine the complex plane, which is what we've been dealing with for the past few videos in this playlist, we can actually take an imaginary input into these functions. And if we do that, if we put an imaginary number inside these functions, we're going to get back our familiar trigonometric functions. So let's do that. So what I'm going to do is I'm going to write x over here, not just as x, but I'm going to write x as an imaginary number. So x is actually going to be equal to I times alpha. And what I'm going to do is I'm going to say alpha is a real number. I'm going to specify alpha has to be a real number. So this notation tells me that alpha is an element of the real numbers. So this fancy r is supposed to be a bold-face r, and that is the symbol for real numbers. So this doesn't have any imaginary component. So if we multiply this real number by the imaginary unit I, we're going to get a purely imaginary number. So we're going to take this version of x and we're going to substitute it into these two definitions, and then we're going to see what we get from that. So let's go ahead and do that for cosine and sine. So I'll do that underneath. So we're going to do it for the hyperbolic versions of these functions. So we're going to have hyperbolic cosine, and inside of hyperbolic cosine, I'm going to input this version of x. I'm going to put I alpha. And that's going to be equal to, if we look at this definition, that's going to be equal to e to the I alpha plus e to the minus I alpha divided by 2. And from the previous videos where we looked at Euler's formula and we looked at writing the trigonometric functions in terms of the complex exponential function, this is actually just equal to cosine of alpha. So we can see that this is cosine of alpha. Isn't that interesting? We can get the trigonometric function from the hyperbolic function if we just input an imaginary angle or an imaginary input over here. So the value that we're putting in, we can think of it as an angle. Though for hyperbolic functions, it's not the same as the angle in the unit circle. There is a slight nuance there, which we won't go into in this video. But these guys can be used to parameterize a hyperbola. That's why they're called hyperbolic functions. Whereas these guys, the trigonometric functions, they can be used to parameterize a unit circle. So whenever we're dealing with circles or oscillations, where we have some kind of repetitive behavior like this, we're going to be interested in trigonometric functions. So that's cosine and sine, and also their ratio, tan. That's the ratio of sine and cosine. And if we're interested in hyperbolic geometries, we're going to take the analogous version of those functions, and that's these guys over here. These guys are the analogous versions. And they're going to help us parameterize hyperbolic geometries. And it's going to be very useful because both hyperbolic geometries and circular geometries with oscillations and those kind of periodic behavior, those both appear very frequently in physics. And that's why this is in the quantum mechanics playlist. We need this mathematical background so we can solve differential equations and actually describe the universe. So now let's go ahead and do the same thing that we did for the hyperbolic cosine and do it for hyperbolic sine. So I'll do that in red so we can clearly see the difference. So let's substitute x equals I alpha into this equation as well. So let's take this. We have the hyperbolic sine of I times alpha. This is going to be equal to, from this definition, we're going to have, I'll leave a little space over here because we're going to have to modify it a little bit. We're going to have e to the I alpha minus e to the minus I alpha. So we've got a minus sign over here instead of a plus. That's just coming from the definition. And we also have to divide by 2. But this is not the same as the trigonometric version of sine. It's not the same function. What is missing? We're missing an I. We need an I downstairs. And if we add an I in the denominator, we have to multiply I at the top as well. We have to multiply the numerator and the denominator by the same factor. So what I'm going to do, I'm going to put this in brackets. I'm going to multiply this by I. So this I and this I can be cancelled out, and that's just going to give us back this definition. So this over here is the same as sine of alpha. So now I can write this as I times sine of alpha. And these two relationships help us translate between hyperbolic functions and trigonometric functions. So this cos of alpha and this sine of alpha, those are the familiar trigonometric functions that we're used to. Those are the guys that parameterize the unit circle. These guys over here, the hyperbolic versions, are the ones that are used for hyperbolic geometries. So now what I want to do is I want to examine what happens when we add these two functions together. So what happens when we add cosh and sinh together? So I just used an alternative pronunciation. We can call this guy cosh and we can call this sinh. So that is just a quick way of pronouncing them instead of having to say hyperbolic cosine and hyperbolic sine, because it's a bit of a mouthful to pronounce all those words and all those syllables when we're frequently saying them and doing derivations. So from now on, I'm going to pronounce this as cosh and this one as sinh. There's alternative pronunciations, but I'm going to go with cosh and sinh, just as kind of like a shorthand notation. So now let's go ahead and add these guys together. So let's add cosh of x and sinh of x. We're going to add these guys together. what are we going to get? Well, if we look at the definitions, there is a plus e to the minus x over here, and there is a minus e to the minus x over here. So if we add these two guys together, this guy and this guy are going to cancel. So e to the minus x is going to disappear. We're just going to be left with e to the x plus e to the x. So we're going to have two copies, and we're going to have a factor of 2. But we also have a factor of 2 in the denominator. So the 2's will cancel, and we're just going to be left with e to the x. So this is equal to e to the x. Now have a look at this. If I take this relationship that I have and substitute x equals I alpha in the same way that we did over here and over here, I can actually recover Euler's formula. Because cosh of x, if we put x equals I alpha, that is the same as cos of alpha. So I'll just put this over here. We have cos of alpha. And what are we going to have over here? Well, this sine of I alpha, that's going to turn to I times sine of alpha. So I also used shine. That's an alternative pronunciation. Shine is sometimes used, and cinch is sometimes used. So there's not really a big consensus among mathematicians and physicists and engineers. People sometimes use shine, sometimes cinch. It's kind of annoying, but what I want to do is I want to expose you to these different pronunciations so that you get used to them. So we have cos of alpha, and then we're going to have I times sine of alpha. And what are we going to have on the right-hand side? We're going to have e to the I alpha. So this is just doing the same substitution. We have x going to I alpha. So this guy gets turned into normal cosine, and this guy gets turned into normal sine, but there is a factor of I out the front. And this factor of I comes from this relationship over here. And here we have e to the I alpha. So this is Euler's formula. So you can see these analogous relationships that we get just by expanding our understanding and going to imaginary numbers. We're expanding our world from the real axis to the entire complex plane. And that's allowing us to see these relationships. Let's see what happens if we subtract these guys. Let's take cosh and subtract shine or cinch. There's two different pronunciations. So let's do that over here. If I take cosh of x and I subtract cinch or shine of x, that's going to give me e to the minus x. Why is that the case? Well, if I subtract this guy over here, we're going to have e to the x cancel with e to the x because we're subtracting this guy from this guy. So those guys are going to go away. This minus sign is going to get turned to a plus because minus times a minus, that's going to give a plus. So we're going to have a plus over here. So we're going to have two copies of e to the minus x. And in the same way that we had over here, that factor of 2 is going to cancel with this factor of 2. So we're just going to be left with e to the minus x. So e to the minus x. Then what we can do is we can do the same substitution trick. So what's going to happen? We're going to have cos of alpha over here, and we're going to have minus I sine of alpha, and that's going to be equal to e to the minus I alpha. And this is another analogous relationship. This is the complex conjugate version of Euler's formula. So this guy over here, e to the I alpha, that is the complex conjugate of e to the minus I alpha. So putting a minus sign in the exponent of a complex exponential is the same as complex conjugate. So I goes to minus I, that is the complex conjugate. And look at over here, we have a real component and we have an imaginary component. That's the same over here. We have a real component and an imaginary component. And we take this I and we turn it into a minus I, that is complex conjugation. So that is the process of taking the real axis and reflecting over the real axis. So you take your imaginary component and you negate it. And that is what happens when you reflect over the real axis. So these guys are complex conjugates of each other. And that is analogous to these relationships between hyperbolic functions, when we add and subtract these hyperbolic functions. So you can see that these guys can actually be thought of as the even and odd parts of e to the x. That's what this cosh and shine relationship is. So if you add these guys together, you get back e to the x. And if you subtract them, you get e to the minus x. So what I also want to show you in this video is an analogous version of a very useful trigonometric identity. So for cosine and sine, we're actually used to having this trigonometric identity. We have cosine squared of x, actually I'll write alpha for consistency, cosine squared of alpha plus sine squared of alpha, that is always equal to 1. This is a very useful trigonometric identity. What is the analogous version of this trigonometric identity for hyperbolic functions? Well, we can find it very easily. What we have to do is we have to transform using this same technique. And what we're going to find is that if we subtract the hyperbolic versions, we're going to get 1. I'll prove that down here. So I'm going to write it down, I'm going to prove it. So let's have a look. If we take the hyperbolic cosine squared, and I'll put x inside as the input, and we subtract off hyperbolic sine squared, and that's actually going to give us 1. I'm going to prove that over here by expanding these definitions. So let's take this definition and put them over here. So that's going to give us e to the x plus e to the minus x divided by 2. And that's going to be all squared. So that is just this hyperbolic cosine part squared. And then we're going to subtract from that e to the x minus e to the minus x. And that's divided by 2. And that's all squared. So what is this going to be equal to? Well, when we square this, this 2 is going to become a 4 because we're squaring the denominator. And we're going to get 4 down here and 4 down here. So we can actually group this into a single fraction. Then we're going to have to expand this top bit over here and this top bit over here. We're going to subtract those guys. So I'll write that out in full over here. So what we're going to get is e to the x plus e to the minus x all squared. What's that going to give us? If we expand this out, well, we're going to get e to the 2x. That's when we square this. We have e to the x times e to the x. Over here, we're going to have e to the minus x times e to the minus x. That's going to give us e to the minus 2x. And then the cross term, e to the x times e to the minus x, that is just 1 by the same reasoning that we had up here. So this times this is 1. We're going to have 2 copies of those. So we're going to have 2 over here. And then we want to subtract from that this version over here. So when we multiply this guy by this guy, e to the x times e to the x, we're going to have this. And when we multiply minus e to the minus x by itself, this minus sign disappears. So we're going to have this same combination. We're going to have e to the 2x plus e to the minus 2x. But here's the different part. When we multiply this guy by this guy, we're going to get minus 1. And there's going to be 2 versions of that. We're going to get minus 1 and then minus 1. That's going to give us minus 2. So we have minus 2 over here. And this is all divided by 4. And have a look at this. This guy, e to the 2x, is going to cancel with this guy over here. So we have a minus sign. If we distribute that minus sign, this guy cancels with this guy. This guy cancels with this guy. It's e to the minus 2x minus e to the minus 2x. And what's left? We have 2 minus minus 2. That's 2 plus 2, which is 4. So we're left with 2 plus 2, which is all over 4. And that is equal to 1. So we've proven that this works. It follows from the definition over here. So this is always equal to 1. So that is the analogous version of this trigonometric identity. This, if we substituted in x equals I alpha, we would actually get cosine squared of alpha, right? Because cosh squared of x, that's just gonna, this is actually the same. These guys are the same function when we substitute x equals to I alpha, as we can see from up here. So what's gonna happen? This guy over here, we're gonna have a minus, and I'll write this out in full. This shine, or cinch, is actually gonna have a factor of I out the front. So I'll write this out in full so you can see what happens to that I. We're going to have I times sine alpha all squared. And this I over here, when we square it, is going to turn into minus 1. So that's going to give us cos squared alpha minus, which is going to turn into a plus, sine squared alpha. And that's equal to 1. So you can see that's the same fundamental trigonometric identity that we have up here. And we got that by substituting x equals to I alpha. So this factor of I over here, that is where all those minus signs are coming from. So that is the only inconsistency between trigonometric identities and those hyperbolic versions of those trigonometric identities. So there's those factors of -1. And if you look up tables of trigonometric identities and tables of these hyperbolic analogous identities to those ones, you will find these pesky minus signs showing up in various places. And the reason you have those pesky minus signs is because when you transform this hyperbolic sign to normal sign, you have a factor of I. And you can see over here, when we put this factor of I down in here, this I becomes I squared, and that is responsible for giving us a -1. So if we multiply -1 by -1, that's going to give us a +1, and so we'll get back our fundamental trigonometric identity. So that is where those discrepancies come from between hyperbolic identities and trigonometric identities. So this video had the aim of introducing trigonometric functions and hyperbolic functions alongside each other. And the purpose of introducing them together is to show you that complex numbers, and particularly putting imaginary numbers into these hyperbolic functions, will actually show you the relationship between them. So that's the important part of this video. You can find other videos just like this one in the quantum mechanics playlist, where we look at the mathematics that we need to build up towards quantum mechanics.